First, I would like to, on behalf of the Institute, to welcome our honorable guest, Rector and Professor Phillis. Professor Phillis, please stand up so we can welcome you.
Thank you.
Well, it's my distinct pleasure to introduce Professor Phillis, who will present his talk entitled How to Define and Evaluate the National Security in an Era of Climate Change. We all know the national security has been challenged, due to this serious climate change. But in which way, how it can be viewed and evaluated, estimated through a very methodical methodologies. I think that is the Greek is famous about methodology. Yeah, so I think it is a distinct opportunity for us to listen to Professor Yannis Phillis' research. His primary research actually in stochastic control and discrete event systems, application in manufacturing, networks in environmental systems. From 1980 to 86, he was with Boston University, Boston, Massachusetts. Since 1986, he has been with the Department of Production, Engineering, and Management in the Technical University of Crete. If everyone remember your probably junior high textbook, 克里特金杯，记不记得在历史上非常有名的古希腊的克里特金杯？它这个就是克里特啊，从克里特过来啊，try to introduce them the history of Crete. Yeah. 那么在这个 Chania 这个 place Greece 在这一省 where he's a professor and the director of the CAM laboratory. In 1992 and between 2005 and 2007, he was a visiting professor at UCLA chemical engineering department. He's in AAAS. AAAS 大家知道是那个 publishing 这个science 这个 magazine 的这个 organization, and the recipient of numerous honors, among which Professor of the Year award at the Boston University in 1986, and an award by the Academy of Athens, 就是雅典科学院 for his environmental activities in 2007, fellow of the Valley Zealous Research Institute in Greece, and the recipient of awards by the municipalities of Chania and City, Greece in 2005 and 2008, respectively, for his service to the Greek society. Professor Phillis was a rector of the Technical University of Crete for about 10 years. Rector 就是希腊字里面的校长 ，rector 就是等于我们的 president of the university. In 1994, funded and developed the 80-acre park for the preservation of flora and fauna in Crete. The park is a laboratory for the study and the preservation of the endangered plant species, which is also actively involved in ethnobotanic issues. The park is visited by thousands of people every year, which we hope you will have opportunity to visit. Apart from publishing the 90 scientific papers and 4 technical books, Professor Phillis is also an award-winning writer in Greece and the US, having published several poetry collections. 所以他是一个诗人喜欢写诗，写这个古典的这个希腊诗。想起我们的余光中余老师最近刚 pass away， 他说天空十分希腊。 天空非常希腊，可是大家有没有记得这一首诗？我们就等一下问他为什么天空要非常希腊 ？Why the sky is so Greek? Well, one of our most famous poet wrote poetry saying the sky is very Greek. If you can tell us why the sky is very Greek, then that means good sky. 那么 He's a senior member of IEEE, a member of Sigma Magazine, the Poets and the Writers USA, the Pen Club, 这种笔会就是世界的笔会的这个 member, and the European Art Center of Athens. I'm very thrilled and delighted to have Professor Phillis here to share his insights with us. I wish all participants can have a very enriching experience, both personally and professionally. Please join us in thanking Professor Phillis for visiting us. Yeah, thank you.
Good afternoon, everybody. Thank you very much, President Frank Chang. First of all, for the invitation to come here to see this great university of yours. And I have to say that the honor is mine, because this place is a great place. It's the first time I visit Taiwan. I've never been to Taiwan. I've been to mainland China before, several times. But from just the small experience I've had so far, by just visiting several laboratories and your famous institute, Technology Institute, and by seeing students showing me projects you are doing, I have come to realize that you are in a great university. And I'm talking about a world-class university. And I've seen hundreds of them in Europe and in North America, and in South America too, where I've spent some time on sabbatical. So I'm really thankful for giving me this opportunity and inviting me here. And, but I have to say something else too, which was very impressive to me, and really I enjoyed it, and I have been enjoying it a lot. Science and technology aside, I've met several people these 2 days, and I was profoundly impressed by the politeness, the openness, and the hospitality of all the people here. It's something you don't find so much in the old world of North America or Europe. It's something that you find a lot here and also in Southern Europe, but not so much elsewhere. And this is really the most important thing, your people, which is your capital in the end. Okay, so I do thank you all, and I do appreciate all your help, the ladies who have been showing me the place around, and the professors who showed me their labs, and students who showed me their projects. Now let's go on with the talk. By the way, after I finish, I would love to have to hear questions, and I would love to have a debate. And I'm talking about debate, okay? So just ask anything you think is something you would like to hear from me and clarify. Another thing I would like to say is that from my discussions, and I've had many these 2 days with many people, students, professors, clerks, employees, many people, I can tell you that this is a country of free expression and a country of human rights, which I enjoy tremendously. And this is not something you can take for granted in many places in the world. So do enjoy it. Okay, let's begin. National security is something that most of us associate with military conflict, war, terrorism, and crime, okay? But nowadays, we live in an era where climate change is, at least in my opinion, and in the opinion of many researchers, the major security threat for nations. And I'm going to explain myself. Let's see some data first. Let's talk about war. War between 1985 and 1994, according to the British Medical Journal, cost the world 378,000 dead people per year worldwide. Terrorism, by another source, between 2006 and 2015, cost us between 20,000 and 33,000 people killed because of terrorist attacks. Climate change, let's see what's happening here. In 2009, the World Health Organization estimated that we would suffer about 141 excess deaths because of climate change, because climate change causes disease and malnutrition. Well, in the same year, the so-called Global Humanitarian Forum raised this number to 300,000 per year because they also added storms and flooding, extreme weather events. In 2012, this number was upgraded to 400,000 dead people per year because of some additional concerns. And the latest papers we've seen in the literature say that by the end of this century, we will be having tens of millions of casualties and deaths annually. So this is the major security threat. And of course, one cannot ignore war and terrorism, but this is the major threat, which, by the way, is ignored by the majority of people. Okay. We don't have an accepted definition of climate security, and we don't have any way of measuring it so far. And this is an attempt we've made. By the way, this is going to be published in a few months in one of the major scientific journals on climate change, the so-called Climatic Change Journal by Springer-Verlag. So besides conflict, we see the national security as a function of other things such as famine, water resources that are endangered, extreme phenomena that threaten all of us. Just 2 days ago, when I left Greece and came here, I saw on the news we had a major flood that caused a lot of property damage in the western part of Greece. And a few months ago, we had an enormous flood just outside Athens that cost several lives and destroyed the whole town. It just flattened it. The town disappeared. And we are having such events almost daily in some place of the earth. All right. Let me show you some common catastrophes which we cannot suspect that are due to climate change. The Syrian war. We all hear about the Syrian war and the atrocities and the bloodshed and all the refugees that are flooding southern Europe, Greece primarily, and then they try to move on to Germany and Scandinavia, but they don't allow them anymore. So Greece is crowded now by tens of thousands of refugees coming from Syria. Okay, what happened there was the following. Between 2007 and 2010, there was an enormous drought, which forced 1.5 million people to move to big cities because of hunger. It's as simple as that. And what happened next is that these cities, like Aleppo and Damascus, suffered an enormous and sudden, abrupt demographic change. The government didn't pay any attention to this. So there was a lot of friction between the people, the refugees, the domestic refugees, and the people of the cities. And then there was civil war outbreak. By the way, this is not my finding. This is accepted right now in the scientific literature. And many political scientists and social psychologists are supporting this idea. So what we are doing, we have developed a model which uses, let me see, does this? Okay. Which uses 7 dimensions, as we call them. I'll show you the picture soon. Water, food, energy, land, conflict, of course, health and economy, which are all associated with climate change. All right. The goal of the model we have developed is to rank countries according to their security standing, and also to identify those policies that have the highest potential of improving, of changing national security positively. Okay. I'm not going to show you the mathematical details. I have uploaded the papers here on this machine. Anybody who wants to see all the details, and it's a lot of statistics and data analysis, and then fuzzy logic reasoning. All these things I have here, but I'm not going to bore you with all these mathematical details. I'll give you just the main ideas. So we use the IPCC approach Do you know what the IPCC is? It's, they even got a Nobel Peace Prize. It's this organization of scientists from all over the world who produce every so many years reports about climate change. And they give guidelines to governments about action. The IPCC is a United Nations organization. It comprises completely scientists. And so they use three components: exposure, sensitivity, and adaptive capacity. Exposure is simply the number, is defined as the number of people or the amount of resources affected by climate change. Of course, always, or almost always negatively. Some assets are impacted positively. For instance, in Siberia, we're going to have more rain, and that means maybe Siberia will become a place where we grow wheat. But also it has another negative point. In Siberia, there are billions of tons of methane buried in the ground. And so if the tundra thaws completely and all the ice is gone, all this methane will go up. And as you've probably heard, methane is a very potent greenhouse gas, 23 times more potent than carbon dioxide. The only good point about methane is that it has a short residence time in the atmosphere. Do you know how long carbon dioxide stays in the atmosphere? Does anybody know that? Students?
Carbon dioxide.
So we don't know exactly, but we know that a portion of that, according to the IPCC, which is the most authoritative group of climatologists, according to that, about between 15 to 40% of carbon dioxide stays in the atmosphere for thousands of years. So if you burn something now, this carbon dioxide has a chance of 0.15 to 0.4 to stay practically forever. We live too little. We live 70-something years on average. So whereas methane stays in the atmosphere something like 12 years. So there's this big difference. Sensitivity is the degree to which a sector of the economy or the society is affected positively or negatively. And adaptive capacity is simply what the word says. It's the capacity of a society to adapt to climate change. For instance, countries that are lying low, as the sea level rises, they will have to build dikes, dams, and whatever else. All right. So, or we'll have to take care of changing agriculture to crops that can stand drought and so forth. This is adaptive capacity. Okay, this is the model. It looks horrendous, but it's not. So what it is, it computes an index ranging from 0 to 1, 0 completely unsafe, 1 completely safe for countries, which we call fuzzy, the model is called fuzzy assessment of climate security. And this is also a definition plus to a measuring device, because that's how we define security. Someone else could define it differently, but there is no other model that measures climate security. There is one by Notre Dame University in the US, but it does a lot less than this. And so, you know, this is the first one that does really a big job in this area. Okay, so here we have the components I mentioned before: water, food, energy, land, etc., up to economy. These are the inputs to this box here. And each of the boxes has these three components, which I mentioned, as IPCC says, which is exposure, sensitivity, and adaptive capacity. And right here we have all the indicators we take into account as inputs to these boxes. And here we have all the data which we collect from national statistics, from the United Nations, from the World Bank, from the Organization of Economic Cooperation and Development, and so forth, from international agencies. And then we do some cookery here, statistical cookery, and then we proceed all the way to this box. This is the basic idea of the model. Anybody, as I said before, who wants to see all the details, I have uploaded all the details of the paper here. And so let's proceed. We take we take an indicator. Let's say we take drought. How do you measure drought? You look at the frequency of droughts. But then, if you look at the frequency of droughts, let's say you have a different frequency of droughts in Taiwan and in Saudi Arabia. It's obvious. So what we do is we don't look at the level of drought, but at the trend of drought. Does this change? Do we have a changing trend, plus or minus, positive or negative? We want to have a negative trend or zero trend of drought to be safe, right? Okay, so we look at the trend of say, droughts, of frequency of droughts, and we collect data for years. We have as many years in the past as possible. Why do we need so many years in the past? We need them so that we introduce memory in the model, because you see, if you take the latest piece of data, let's say 2016, TK is 2016, and let's say this year was very good for a country, then you get the wrong idea. You have to look back, as far back as possible. So we went and collected hundreds of thousands of data points going back to the past to see what the trend was for each country, for each indicator. All right? And so we have, as you see, for the present time, and then we go back until to some year T1, which I don't know which one it is, given, but we find it from the data. All right, and so we have the years, and we find, as I said, trend estimates, but also level estimates. Why do we need level? Let's say that we talk about carbon dioxide concentration in the atmosphere. There you don't need trend, you need the level. How much you have now? Whatever you have now is going to determine how warm the climate will become. Therefore, for some indicators you use the level, for some indicators you use the trend, so that the model produces something sensible. Otherwise, you won't get anything reasonable out of it. Okay, and what we do next is we compute. There is an algorithm that does what we call exponential smoothing. Exponential smoothing is simply predicting the past in some sense. What do I mean by this? Going to past data and trying to see how things move in a smooth way. But past data have to be decayed as you go more and more to the past. So you have an exponential component, e to the minus t, multiplying each piece of data as you move backwards. And so you say memory decays as you move to the past. So we do that. We have an algorithm which computes level and trend. It's a standard statistical algorithm. I'm not going to, as I said, to bore you with details about that. It's called the Holt-Winters algorithm, and so for each piece of data, for each indicator, we compute this or this, and then we use it as an input. All right. The next thing is you have indicators that are strange. You have, let's say, frequency of droughts. You have number of deaths. You have GDP per capita. Those are strange things. You cannot combine them together, right? You cannot add GDP and frequency of droughts or sea level rise or elevation of a country if it's low or high. Those are very strange things. So what we do is we pass all the data through a filter that normalizes them on a scale from 0 to 1. 0 means that it's completely unsafe. 1 means it's completely safe. And how do we do that? Let's see. These are straightforward, straight lines. It's very simple, trivial equations. Let me show you the picture. If you have an indicator that the indicator becomes safe when it is as small as possible. Small as possible means you have an indicator to have the value of 1. It has to be below some level, okay? And then it goes down to 0 linearly. Linearly because this is convenient. There's no other reason. Nobody told us it should be a straight line. Yeah, but it's okay. Let's take again the trend for of droughts. Okay, the trend should be 0. So then you say anything smaller than 0 takes the value of 1. If you find a negative trend, that is droughts are disappearing and you have less and less and less and more precipitation, then you have safety of 1. And if you have 0 and then you go to positive numbers, then you have less and less and less linearly until you reach 0. Okay? How do you specify these two limits? You specify them by experience or by standards that have been adopted internationally. For example, when we talk about emissions of carbon dioxide, we go to the so-called Paris Agreement and see what the agreement, have you heard of the Paris Agreement?
Yes.
It's an agreement that was signed by almost all the countries of the world. Right now it has been signed by all of them. It has been ratified by all of them. Only the United States is pulling out suddenly. And this agreement was signed in 2015 in December and ratified in 2016 by all the countries of the world, and all the countries made the so-called INDCs, the intentions to cut down emissions of carbon dioxide and, in general, greenhouse gases. Okay, so we go to this agreement and specify the limits they've put there. Or we go to other agreements of the United Nations or a country. So that's how we specify these numbers. Here we have a situation of something that has to be as large as possible, not as small as possible. Let's say that we talk about GDP. We need GDP per capita because GDP per capita is associated with the adaptive capacity of a country. If you have a poor country, it cannot adapt because they don't have the resources, right? So you need as high as possible. GDP is one of these cases. And then you have something in between, something that cannot be too small or too big. Let's say we take the energy efficiency of producing $1. Energy efficiency cannot be 0 and cannot be too big. It has to be somewhere in between. And to define the two limits of energy efficiency, that is the amount of energy you spend to generate $1, we thought that the best way to handle that would be to look at the Scandinavian countries. So we looked at the best and worst of the Scandinavian countries, and that's what we did. This is a little bit arbitrary, but there's nothing else we could possibly do. Okay? So that's why we have these three situations. We pass all the data through this filter, and then for each indicator, we have a number from 0 to 1. And then you can do anything you want, because all the numbers do not have dimensions. They're the same, and they're all equal. All the animals in the zoo are equal, and we proceed. And then what we do, we start with the data. We go through statistical analysis. We go through normalization. Then we move on to falsification. Students, have you heard of fuzzy logic? Yes, no? No, you haven't? You haven't. How many of you have heard of fuzzy logic, of the students, I mean? No one? Look, let me say this to tell you what fuzzy logic is about. You want to park your car, right? You want to park it. You say, all right, here's one car, and here's another, and here's the space. What I'll do, I'll stop the car somewhere there, and I'll back up, correct? You don't solve differential equations. You could do it, solving differential equations of motion. You use Newtonian mechanics and you park the car. You put some performance measure, you know, distance, etc., but nobody wants to do that unless you have a computer, okay? So what you do is you say, okay, let me stop somewhere in front. How much in front? Well, a little bit more than this car here, and then what do? Is I aim at the middle of the space. Okay, so I turn my steering wheel. How much shall I turn the steering wheel? A little bit. So much that I can hit the middle of the space. This is fuzzy logic. You think not in terms of mathematics, but in terms of a little bit more, a little bit less, and that's it. And then you say, okay, now let's press the gas a little. How much shall I press it? Not too much, but not too little, slowly. So you back up. Then you see that you've turned your steering wheel too much. Okay, let me turn it to the left a little more, a little, and so forth. A little more, a little less, and you park the car. Or how do you shoot the ball when you play basketball? You give it some force, right? Okay, and the ball makes some kind of parabolic trajectory, and it ends up in the hoop. Those geniuses like, in my days, Larry Bird and Magic Johnson, or later on Jordan, and today, I don't know, LeBron James, what do? They say, they have some microchip in their heads. They say, let's press so hard the ball and give it this direction, and bang, they make the hoop. I cannot do that. Most people cannot, but they can. But what they do is they do fuzzy logic control, fuzzy control. They control the ball, the trajectory, and the force. We do that every day. Every time you cook your food, how much salt are you going to put? Well, you don't have a precision scale. You put a little bit. You taste it, it needs a little more. You put a little more. Okay, that's what we do here. We say, let's say that a piece of data is right here, this one. This one is, you see the range is from 0 to 1. 0 is unsafe, 1 is safe. Okay, then you say this one is medium with degree of belief, this is the fuzziness, with degree of belief of I don't see here, of 0.312. It's a straight line. But also it is weak, W means weak. It is weak with degree of belief of 0.635, 3 whatever, whatever it is. Okay, I cannot see it very well from here. So you take all the data, and as we say, you fuzzify the data. And then, after you've done this, you move on with the model, and you say, and you have what we call rule bases. What do these rule bases do? They say that if I have an input 1, let's say again drought, that is poor, and precipitation that is average, etc., then you might say the sensitivity of water security is average. This, if this is so and this is so, then that is so. This is a rule. That's what we call a rule. All the set of all the rules, the possible rules, is the rule base. Okay? Now, what you do is you do, again, some simple arithmetic, very simple arithmetic. I'm not going to get into that since you are not familiar. I'm talking about the students, of course, not familiar with fuzzy logic. But I can tell you that this product here and this summation here have a very profound secret behind them. If you don't do these two operations, and I have in the paper all the references, then you might run into a situation whereby if you improve security of indicators, each indicator, you might end up with a worse outcome at the end, which is completely wrong. So this guarantees monotonicity, this and this. They guarantee monotonicity. If you improve the input, you improve the output. In fuzzy logic, things work in a strange way, and sometimes in an extremely nonlinear way. We have proven a theorem that says that if you take product, and if you take sum, and if you use what we call triangular membership functions, you know, triangles, and if you use the so-called height defuzzification method, that is, from the fuzzy result, you get a number in the end, because that's what you want to get. You want to get for each country a number from 0 to 1. Is it safe, unsafe, how much safe it is? If you do these things, we have proven a theorem that says that the model is monotonic. If you use something else, and we've blundered in the beginning, then you might get very strange results. Okay, and so in the end, you get a number for each country, which tells you how safe the country is or how unsafe it is. And then you rank all the countries accordingly. I'll show you the results soon. All right, the other thing you do is you perform what we call sensitivity analysis. How do you do sensitivity analysis? By taking derivatives. You take a derivative of your outcome with respect to one of your inputs. Okay, and what are the inputs? My indicators, x1, x2, etc., etc. What you do is you perturb one indicator by an epsilon, a small amount, and you divide by that epsilon. And this is an estimate of the derivative, of the gradient of security with respect to this indicator xc. Let's say that this indicator is number of deaths because of climate change. Okay, you find out how unsafe or safe this thing is. Okay, and then, but if you get a derivative, if you and you rank indicators according to derivatives, you run the following risk. If you have a curve that goes up like this, but it's way down, and you try to improve it, this has a very high derivative because it's going up sharply, right? The derivative is high. If it's low and you focus on this and you put your money as a government into improving this indicator, you've done the wrong thing because this is a very low level indicator. So what we do is we multiply this estimate of the derivative with 1 minus x. What is 1 minus x? It's the distance of the indicator from the safe region. So then you have a much more reasonable estimate of your priorities. And what we do this way is we find the priorities of each government in each country if they have the resources to do that. Now, if you take second derivative, that is you perturb two indicators, you can find two important indicators, three and so forth. We've stopped at two. And so now, after this, okay, let me show you just as an example some of the indicators. Here we have water. This is one of the dimensions. And here we have exposure. And we say exposure is estimated via precipitation, frequency of droughts, and sea level rise impact on rural land. Because as the sea rises, it destroys land, of course. And when it destroys land, it destroys also water. It becomes saline. Water gets salt. So, and for precipitation, we use the trend. For frequency of droughts, the trend. But for sea level rise, we use the level. Because it doesn't change, you know, the level goes up, up, up all the time. It doesn't, there's no trend to be discussed there, and so forth. And here we have the various values of the filter I showed you before, and in another place we have also the sources where we got the data from. And usually, as I said, it's World Bank, United Nations, places like this. Okay, and then when we talk about sensitivity, we have water withdrawals, how much water you draw, is it sustainable or unsustainable, and so forth, and forest change, because forest change is connected with water resources. If you denude a place, rain does not percolate. You don't collect rainwater, and so forth. Okay, so these are some of the indicators. I have them all here. Anybody who wants to get them, I would be more than happy to send them to you or copy them from here if this is possible. Okay, and what we did is we ranked 187 countries. The number of countries that signed the Paris Agreement, I think, was 193, something like that. But some of the countries were in disarray and we couldn't get data, such as Somalia or Syria. So we had to exclude some of them. And we went to 187 countries. We collected, we went back to from 1 to 114 years, depending on how many numbers were available from all these agencies. And we collected overall 195,000 values, all right? And then we did all the processing of the model, and we found out that the top 10 places, the safest countries in the world, are occupied by European countries and Australia. And if you go to 20 top places, then you add also Canada and USA and New Zealand. And the most unsafe countries, the most vulnerable, are the Sub-Saharan, Mauritania, Somalia, South Sudan, Seychelles, and some small island developing states which will disappear in a few decades. The Marshall Islands, Tuvalu, the Maldives, Micronesia, and some other countries too are going to disappear. In fact, they have plans right now of moving those populations to other places. Okay, and here we have all these countries in succession according to their safety. Number 1 is Finland, as you can see up here. Number 2 is Austria. Number 3, Sweden. Number 4, Norway, etc., etc. Then we go down number 10 to Australia. And here you can see the most important aspects where they have to pay attention if they want to improve things. And here, if they have the money and the resources to improve two aspects of climate security. As you see, in Northern European, it's, the most important thing is population of people of ages above 65. Now let's see that. Let's see what this means. It means that they have an aging population, which is well known. But what can they do? Can they make people younger? Answer is no. But if they have money, they could improve their adaptability to climate change. That is, if we have hot spells or very cold spells, as we're having right now in Europe, then you have to take measures. You have to have hospitals, you have to have places that are air conditioned, you have to have health provisions for these people, for the aging population. And then you can see that if you have two components you could possibly improve, then the second one would be renewable electricity production for Finland, all right, and so on. Sometimes this thing is found here. Sometimes this thing is not found here because the model is non-linear and the second derivative does not necessarily give you the first derivative. It doesn't incorporate it because of non-linearities of the model. Okay, and so we can proceed like this. You can see that the United States is down here. It's number 18. And Japan is number 26. Japan has some problems. One is the population. The other one is sea level rise impact on population, because it has a lot of areas surrounded by sea, lying low, and these places will be affected. So here we found it using the model and the data supplied by the country. And my country, Greece, is where? 48, somewhere here. Here, it's 48, and the most important factor is GDP per capita. About 5-6 years ago, it would be renewable energy production, but right now it's GDP per capita because of the economic crisis. The country is going bankrupt, and without money, you cannot solve any problem. We all know that, okay? So that's what the model showed us. All right, the model also unveiled some other interesting things. For example, let's look here. Number 21. Number 21 is Uruguay in Latin America, okay? It's better than Denmark. And of course, this comes as a surprise. How come Uruguay is better than Denmark? Well, we looked at all the steps of the model and the data and the intermediate results, and we saw that Denmark is inferior to Uruguay in terms of renewable energy and in terms of water resources, much worse than Uruguay. Therefore, it's ranking. And also you can see that it's Uruguay better than Japan, again for similar reasons. And then you have Costa Rica right here, who is better than Greece and Cyprus and so forth, again for similar reasons. So, you know, some things are obvious or some things are intuitive, let's put it this way. Some things are non-intuitive at all. Okay, so we found all these things, and of course if you go down to the bottom of the list, you see all the poor people of the world. You see at the very bottom Somalia, Mauritania, the Maldives because of sea level rise impact. And in fact, that was shown by the sensitivity analysis we perform. As you see, it's everywhere the most important thing they have to pay attention to. And then Marshall Islands, which also has sea level rise as the most important factor. It's going to disappear too, and so forth. And then you have also the very poor countries, such as African countries, Gambia, Guinea-Bissau, Democratic Republic of Congo, and so forth, and some countries elsewhere, like Kiribati, Afghanistan, and so forth. Okay, we did our job. We found the ranking of each country according to this model, which also defines national security vis-a-vis climate change. And here we have summarized all the results. We have North America, which is, it has the, as a group of countries, it has the highest level of security. If you look at Europe, the Scandinavian countries are the best. You can see here 0.8. And then if you look at income, the high-income countries of the Organization of Economic Cooperation and Development have the highest level of security. Then you have the upper middle income, then the lower income, and of course the very poor. By the way, high income means more than $12,500 per capita per year. Middle income between $4,000 and $12,500. Lower income below $4,000. And low income, the lowest income is below 1,000 per year. Okay, so that's that. And so we formulated a model that ranks countries, defines security, and does sensitivity analysis. Now, from this, we say, or we claim that climate change is the major security threat for the world. Okay. Now, we have been playing with the climate for the last 200 years without thinking about it. And I am saying that it is time now for reckoning and action. So I'm going to show you something slightly different than this. In these three publications I show you here, we've done the following. We took about 100 differential and difference equations. Those are dynamic systems equations to model emissions of greenhouse gases into the atmosphere related to economic activity. And we took some ready models, of course, by economists of neoclassical economics that show how much economic output you get for a given rate of growth per year. And what we try to do is we try to optimally control emissions so that you maximize something. And what do economists usually maximize? They maximize utility, as we say. Utility means it's a function of how much you consume in some sense, because supposedly with consumption you gain some satisfaction in life. Okay, we did something slightly different. We found a paper in social psychology which shows from experiments that people become happier as they spend more and more, but at some point they reach a saturation of satisfaction. And after that, satisfaction goes down. In other words, if you are a multimillionaire, in all likelihood you are unhappy. So don't become multimillionaires. Okay. And you know, the cutoff point is $36,000 per year per person. Okay, so if you have a family of 4, this is about $130,000, $140,000, which is quite good, isn't it? If you have so much money per year, it's okay. After that, you start becoming unhappy. So we took this kind of measure to optimize. Okay, we didn't optimize the neoclassical utility they use. The more you consume, the happier you are, because this is senseless. Okay, and we tried to see what sort of cuts in emissions we must have to do what? To achieve the goal of the Paris Agreement. What does the Paris Agreement say? It says that all countries will do their best to contain temperature rise to plus 2 degrees Celsius above pre-industrial times, roughly speaking above 1900, very roughly speaking, okay? Right now we have about 1 degree on average worldwide. We're at 1 degree above, so we have 1 more degree to go to reach these 2 degrees. And we say, okay, let's do that. Let's do it optimally and see what happens. All right, so here the red line shows you the emissions per year of billions of tons of carbon by China. Okay, and the green one is the emissions of billions of tons of carbon per year by the United States. and the yellow one is by Western Europe and so forth. Here are the poor countries. They don't emit a lot. They emit very little. All right, so look what happened. We used what we call optimal control theory. There is a theorem there that says what to do and how to do it. Again, I'm not going to go into mathematical details, okay? And we said that if you do it optimally, you have to cut emissions like this. In other words, you don't become unhappy. You optimize your satisfaction from your consumption, okay? How much money you make. All right, and we can go down to the year 2065, and here emissions must reach zero. Emissions from fossil fuels, okay? Because those are the emissions that are bad. If you burn this piece of paper, this is not as bad because this paper came from a plant, and the plant was there, we cut it, then we'll replant it, and this carbon dioxide will be reabsorbed by the plant, okay? But fossil fuels, which means coal, gasoline, diesel, and natural gas, this is carbon that is inside the crust of the Earth, and you pump it out, and it stays in the atmosphere, as I told you in the beginning, for hundreds or even thousands of years, changing climate permanently. So we found that these are the trajectories, but the important thing is, let's see what these trajectories do, or rather, let's see something else. Let's see what happens for per capita emissions. Per capita emissions, although China is #1 in total emissions, you can see that per capita is down here. China doesn't pollute as heavily as the United States. The United States has the record of pollution because per capita, they emit a lot. You know, those of you who have been in the United States, have lived in the United States, they know that the most precious item for an American is what? The automobile. Americans cannot live without an automobile. Also, in the summer, you can see the thermostat being set at about 15 Celsius, but in winter, it's at 22, 23 Celsius, even 25. I've seen it. I've seen it in hospitals myself. And, you know, I cannot stand this thing. I have a tremendous sensitivity to hot weather, and so, or to hot atmosphere. So the Americans burn gas and natural gas and coal like mad. Okay, that's why this thing here. Whereas the Chinese burn a lot less per capita. The Europeans burn something in between, the Europeans here. And these are the trajectories per capita that should be followed optimally. Now let's see what this means. Now this is the most important thing. What is going to happen to the temperature? The temperature, oops, what did I do here? Okay. Yeah, I pressed the wrong button. The temperature, you can see, by the way, we started the control at year 2015, okay, because that's when the agreement was signed. And you can see that the temperature goes up to 2.7, not 2. And you can see also the slope is positive. It doesn't reach saturation. It goes up. It continues. So by the year 2100, we're going to have 2.7 if we act optimally, and we'll go up, 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 and we might stabilize at around 3 degrees, 3.5 degrees. Now, with +1 degree right now, we have all these extreme phenomena we have been experiencing. Imagine what is going to happen when temperature goes up this much. Now, let's see what happens if China and the United States follow their pledges they made in Paris. What will happen is that the trajectories of China will be like this, and the trajectory of the United States like this. The remaining countries we left at the optimal points, okay? So this is what the US pledged to do, and this is what more or less China pledged to do. I say more or less because they didn't give numbers. They spoke a little bit in generalities, but they are doing their utmost to introduce renewable energy. And this is true. Now let's see what happens if we assume negative emissions. Negative emissions means that we have the technologies to remove some of the carbon dioxide from the atmosphere. I saw in some laboratories here in your university, I saw some people developing technologies to remove carbon dioxide. But I have to say this, There is no technology, at least right now, in realistic terms, speaking in realistic terms, that can do a reasonable job worldwide in any sense. You can do it locally, you can do little, but not much. You can capture, say, carbon dioxide in the smokestacks of power stations, and then liquefy it, and then compress it and push it down into the earth. But that would need also tremendous amounts of energy, and the scale is enormous. So right now, we don't have any technology, but let's assume that we do. We find in the future. If negative emissions are allowed, this is a mathematical problem of optimization. You say that now your variables can go below zero. So then, optimally, you have trajectories that go below zero. Negative emissions, right? And this is China. And now action is taken in 2020 because you have negative emissions. And Paris Agreement, by the way, does depend on negative emissions. They all knew that without negative emissions, the 2-degree goal is elusive. They're not going to achieve it no matter what, no matter how hard they try. Okay, so with negative emissions, you can see that we reach the year 2060 to 2065, and we go down below zero, and all countries go below zero except for a few that emit very little. Those are the poor of the world in Africa. So with this, what do? We go up to 2.5 degrees, and we stabilize more or less. But again, we overshoot the goal of 2 degrees Celsius. I've spoken to many specialists in the field. They all say that we are going to go up to 3 degrees Celsius by 2100. That's what they all say. But this is if we take action. If we don't take action, there is a lot of uncertainty, of course. Okay, nothing can be taken for granted. But they say that we suspect that things might get much worse. Okay, so this is what these graphs are telling us. And what is the conclusion is that we are running out of time. By the way, the Paris Agreement had another clause. They said, and we'll do our best to contain temperature rise to 1.5 degrees. Why did they say that? Because with 1.5 degrees, some small island nations will not sink. And to satisfy them, to make them sign the agreement, they put that clause. But this was, in my opinion, if you want my sincere opinion, was hypocritical. Because they all knew that this is unattainable. So, and the 2 degrees is something very, very hard. It's not unattainable. The probability of achieving it is not zero, but it is very low. So every day that passes and we don't take action, and the action should be primarily mitigation, then national security will be endangered to unprecedented degree. I have to say that, unfortunately, most countries in the world, even today, even now as we speak, are putting a lot of resources on getting new oil resources from the ground. They are doing it in Greece, they are doing it in Cyprus, they are doing it in Israel, in Canada, in the United States, you name it. And this is what I call, how is it called in psychology? Cognitive, something like contradiction. That is, you know something is bad, and you promise to do something about it, and then you go on and you do the opposite. Like you know that smoking causes cancer, you tell the doctor, yes, I know it, doctor, and I'm going to be good, and then you go out and you open a pack of cigarettes and smoke like mad, okay? So that's what it is. It is cognitive disagreement, and unfortunately, this is the situation nowadays. Let me say one last thing, and I'm closing, and then I'm open for discussion, that it has been estimated that to reach the plus 2 degrees Celsius of the Paris Agreement, we would be allowed to emit something like 800 billion tons of carbon dioxide in addition to what we have right now. Annually, we emit about 36, roughly speaking again, 36 billion tons of carbon dioxide worldwide, okay? With all the existing reserves of coal And oil, we have about 932 billion tons of carbon dioxide. So even if we exhaust what we have, we don't look for anything more, for no more fossil fuels. If we just burn what we have right now, we'll overshoot 2 degrees a little bit. By searching for more oil and more coal, that means that we simply are trying to do the opposite compared to what we have already signed in Paris. And this is really something that we don't know what sort of effects we'll have, but we know that it's not going to be a happy world. Okay, that's what we do, and thank you very much for your attention, folks.
Professor Phillis, this is a very nice talk. I really enjoy it. Another bad news is it seems we are homeless.
We're hopeless.
Yeah, because even under the Paris
Yes.
Yeah, but the good news is I only have 2 or 3 more years, so it seems that I don't have to really care about that. No, just joking. I mean, for the whole model, I think the very fundamental one is how you choose the factor. So it seems to me that maybe the human factor is not taken into control. Just like say
human factor, human factor like what?
Just like if we someday there's a dictator. I mean, just like if we have a new president like Trump.
Yes.
And they might change the whole policy, and maybe in China there's something happening.
Yeah.
So that may be, in terms of this kind of scientific, I'm not talking about a scientific thing. I'm talking about how to achieve the goal. Maybe it's more important to have. I'm not quite sure how to promote this kind of. I mean, to say just like our president just mentioned that. Most of our young guys, they don't care about this kind of air pollution. Maybe it's too far away from daily life. So do you have any good idea on how to really promote and have an effective way, just in terms of very cold scientific evaluation?
Well, thank you very much for the question. It's an exceptionally difficult question. How to, let me rephrase it, and please tell me if I'm correct. How to make people take action, right? In 3 words. I'll tell you. I don't have the answer, first of all, but I'll give you an example. How many of you, and please pay attention, how many of you would be able to live with 1 shower a day that lasts 90 seconds only, no more? Pay attention, please. Plus 1.5 liters of water for drinking, no more. Plus 5 liters of water to wash dishes and clean your clothes. Plus only once flushing your toilet, only once, no more, per day. How many of you would be able to do that? Nobody, right? Well, I'm telling you, in Cape Town right now, this is the quota of water they have. Why? Because they had a 3-year drought. It hasn't rained in Cape Town at all. And on June 4, you can check the web if you want, on June 4, the mayor of Cape Town in South Africa said that he's going to close the taps completely because they don't have any water left, no reserves. And right now, the people in Cape Town are allowed only this water quota I mentioned, number 1. Number 2, 300,000 people working in the farming industry lost their jobs. And tens of thousands of people will lose their jobs working in restaurants and hotels, because who's going to visit Cape Town anymore if you don't have water, right? Okay, and many people, thousands of people of Cape Town are moving to the US, Europe, and other places of South Africa or Africa. They're moving. And this is something that's happening right now. These people will soon realize that they must take action about this. They've done, and now I'm coming to your question. And again, I'm just thinking aloud. Okay, I don't have the answer. Right now, they've done some research in which they show how neurologists have done that and psychologists have done that, how people change their attitudes towards climate change when a natural disaster hits their area, and how this thing goes away. What happens is that the brain, because of evolutionary reasons, because that's how we evolved, does not remember bad things for too long. Okay? When your mother and father die, you are sad for a day, a week, a month, but you cannot be sad for the rest of your life. You won't survive, right? Okay, if you have an accident, a bad accident, and you lose your leg, you will be sorry for a little bit, but you will recover in no time. It's amazing how fast people who have had bad accidents recover and they resume their lives normally. Okay, this is evolutionary. This is in our genes. So what happens is that if you tell people, imagine what's going to happen to our children and grandchildren 10, 20, 50 years from now, they say, I don't know, I don't understand that. I simply cannot understand it. Okay. Also, when people hear people crazy like me, or you're not crazy, but like President Chang, who spoke very wisely, and I thank you for your words, they become numb and sometimes tired. And they say, okay, we heard that sermon once, twice, 3 times. I got tired. I don't want to hear about that again. This is how the brain works. It's only a few people who move things forward. Just a few people who stay on, who stay focused, and they try to do their best. And for instance, people in the United Nations did their best. And they try to do something really good for humanity. And many people see that this is indeed the right course. And there are thousands right now of scientists who are working in this field, and they are doing marvelous work. And not only for the academic glory or for the money, but because they want to do something good in this world. So now, these are some of the reasons why we don't take action. How to change that? Psychologists have been struggling with this for decades now. They have devised many ways. It's a very, very difficult question. I think that humanity will start acting when they see some big catastrophes, as we witnessed in Greece. Okay? And by the way, I did an opinion poll in Greece. I sent some students of mine, and I found out that the answers were as follows. Is climate change a dangerous phenomenon for Greece and the world? And they said, for the world, the majority said yes, but not for Greece. Why? Because Greece has to look for hydrocarbons because the economy is bad. They think that our country could be excused. You know, they don't understand that we're in the same boat and we'll all sink together. So it's a very difficult thing. For me, what we can do is we can continue doing scientific work. You know, with science comes enlightenment. We should continue doing scientific work, and the climate community is doing very well. I have to say that. And all academies of the world, all without exception, are in favor of doing that. All scientific journals are in favor of doing that, including Nature, Science, and many others. And almost all scientists are in favor of what we're discussing today. And this is the best we can do and hope for the best.
Professor Phillis, I just want to maybe focus on the optimization process you actually did to get those few plots that you show us. I was wondering, when you did all that calculation and modeling, because we all know that the United States is going to pull out, or has already pulled out.
No, it hasn't. They cannot. The agreement has to have a delay. You cannot just say, tomorrow I'm leaving, goodbye.
Okay.
Yeah.
But given the fact that their intention is not to join.
Yeah.
So my basic question is, when you did all that calculation, did you consider the impacts or effects of having the United States eventually pull out of this Paris Agreement efforts? Yeah. And if you consider that possibility in your calculations and include the effects in your modeling efforts, I want to know, do you so far have any quantitative results on how negatively that would affect the ultimate temperature goal we want to achieve? Yeah. In other words, instead of either 2.5 or 2.7 degree as your ultimate goal, with the United States not making any contribution at all, And if you include that in your modeling, what kind of number are we going to get as far as that temperature is concerned?
Okay. Yeah. No, we did not, because number one, although the president said that he is pulling out, he cannot pull out in a day. It will have to be a time span of, I don't remember, 2, 3 years, 4 years, something like that. But the most important thing is the following, that the mayors and the governments of most cities and parts of the United States, states of the United States, have said that we're not going to follow what Trump is saying. And also the renewable energy industry have a big boost in the United States, and they are using renewable energy all the time. They're among the first to use electric cars. And California has some of the best standards worldwide in terms of mitigation. Therefore, what Trump says might turn out to be just hot air, nothing more than that. Because again, of what I said, also some district attorneys are taking Trump to court because of what he is trying to do. And therefore, it's a very complex situation. But to use a simulation whereby we remove all that, the curve of the United States would be unwise, because there is already a trend in the US of emissions that is flattening and going down. It's going down, and it will go down more and more. Just because of the introduction of electric cars, the intensification of renewable energy, and because, as I said, many mayors and many governors of states have said, forget it. You go do whatever you please, but we'll do what we think is right. Therefore, I think that what the simulation showed is more or less right, okay? And so I'm not so much scared by what Trump is saying regarding this. And of course, we'll have an election in less than 3 years, and who knows? Okay, so yeah, that's just not to be always negative. Okay, but thank you.
I want to, maybe this is a follow-up question of what the gentleman,
yes.
First question raised by the gentleman. Because I think his concern is what can make people to change the way they look at this sort of issues, right? My question is, like, because when you show the ranking list, I deliberately look for the information, the ranking information on China.
Yeah.
And if I wasn't mistaken, I saw I think the primary sensitivity factor was political rights.
Yes. Yes.
I was right?
Absolutely, yes.
So that was interesting to me because your modeling approach is quantitative, of course, but it's more geared towards hard data, right? So my gut feelings about the appearance of political rights as a factor is that in your model, you actually have to consider cultural and political factors in the way you model the system. Now, my question is, to what extent did you treat political rights as one that you considered? I can see that on the ranking.
Just a moment, yeah.
My question is, to what extent, how extensive an effort you have actually made to include other cultural factors in your modeling? For example, I'll give you an example. Because you mentioned the typical American lifestyle is to keep the keep the AC temperature reasonably low in summer, even in winter. So this is the kind of thing I talk about. Cultural aspects like lifestyle, cultural norms, cultural habits, cultural values, cultural traditions. When it comes to traditions, we can say, let's say in Taiwan, we have a lot of people worshiping Buddha. and they won't think twice to burn incense and paper monies
True.
to worship their whatever god they consider to be worship.
Listen to our speaker.
Yeah, so please comment on this.
Okay. Now, first of all, I have to say that let's see where we have political stability and, for instance, you can see here in the conflict dimension, we have political stability. Political instability is one of the reasons why we have wars sometimes. Okay, I'm not saying that you necessarily have it, but we know that from Syria, we know that from Africa, we know that from Turkey, from many places. All right, let me see, nowhere else. It's only right here, political stability. For this kind of component, we have data. There are institutions, the United Nations and other institutions, that for each country give you a grade in terms of freedom, political rights, and corruption. There is an international index called the Corruption Index per country, ranging from 0 to 7. And so we had data. What you mentioned is important, but we don't have data. We don't have authoritative data, but we have proxies for that. Let's talk about lifestyle in the US. Lifestyle in the US, you cannot grade it, and we don't have any number for that, but we have numbers for emissions of carbon dioxide, which is a byproduct of your lifestyle. Okay, we have pollution in terms of NOx, oxides of nitrogen. Okay, and again, this is part of lifestyle because you get a lot of nitrogen oxides from cars. Okay, and also from electricity generation. And again, those are proxies of consumption behavior of the US, of China, of Greece, of Europe, etc., etc. But the main thing was to have numbers which would be authoritative and not just start guessing. And for political rights and for corruption, for things like that, we have a lot. And by the way, they revise them every year. And every year they publish a list of all the countries with a grade, and you see how countries behave. And usually the most corrupt countries are in Africa, in Latin America. Also Greece ranks badly in terms of corruption, not very well. And the best data for corruption, for instance, is in Scandinavia, as expected. And then you have political stability. Again, you have similar numbers for all countries, so that's what we do. We didn't want to get into murky waters and start playing with things we don't have anything to handle, okay? And it was very easy to include it, especially in the case of conflict here, okay? Because political stability and conflict are, you know, and we do know that in China they have conflict with Tibet, for instance. To mention just one thing, not to mention the South China Sea and so forth. Okay, so, and of course, not to mention Taiwan. Okay, and in Greece we have a conflict because of Turkey. Turkey objects to the sovereignty of Greece over the Aegean Sea and the Aegean Sea Islands. Although we have international agreements, they say, no, the agreement must be revised, but the agreement was signed in 1922. Yeah, but we have to revise it, they say. Things like that, you see, and those are the points that create instability and might create conflict. And conflict is part of security.